Look, he takes some initial concentration of these and he takes 0 HI. And then the equilibrium concentrations are 1.14, 1.12 and 2.52. Next time he takes some other concentrations. He takes this and again 0. He gets a different set. He gets a different set. He takes another set and he gets a different set. He takes the thing I was discussing, that he takes more of this and then he gets a different set. One thing is very clear, that each of the equilibrium concentration is very, very different. Of course, sometimes the ratio here is same, is 0.86, 0.86, 0.345, 0. Because that happens according to stoichiometric coefficients. This starts breaking. Actually, the equation is H2 plus I2 to give you 2HI. So it's like this. If you take some value here, if you take some, like he's taking 3.04 initially, and he has got 2.35 after some time. That means 3.04 minus 2.35 was decomposed. So half of that will come here and half of that will come here. I hope you understand. Anyway, don't go into so much detail. The point is that the stoichiometric coefficients are deciding something, and the initial concentration is also deciding the equilibrium concentration. But how come each time you get something different? So what's the constant? Now there is something in which we call as the equilibrium constant, and that is you can't, if you divide the ratio not by any nonsense way, any way doesn't work. A specific concentration will give you a constant value. This is called the equilibrium constant. That means for each equation, there is a constant which is dependent on a particular formula. Now I will go back to, you see, this is what I was, this is like this. When I said, the rate of any reaction is K times A into B, like I'm taking this. This is the rate of the forward reaction. I'll put A, and actually it's not A and B, but I'll put A and B. So this is uh, K times A forward reaction is equal to, I told you the rate, this is the rate. So this rate is equal to the backward reaction. That is what happens. This is the forward reaction rate, and the backward reaction rate is Kb into C into D. Now, what happens is, if you see this formula, this has got, I just now showed you this formula. This has got product over reactants. So I'm going to do the same thing here. So these are the products, C by D, CD, and if you divide this by AB, and you get KF by KB. Okay, so actually what happens is that late clear principle is based on this. If you reduce this, this also reduces to keep the equilibrium constant fixed. The rate, the not the rate, the equilibrium constant fixed, and these two are dependent on temperature. These two. So this ratio, if you don't change the temperature, then these are constant. But the only way you can change is like through concentrations. But for endo and exo, different things happen. This changes because the temperature wo jo we were changing in the previous question. Then this changes, so different ratios, and this is actually dependent on activation energy. Because I won't go into details, because no, in the, if this is the activation energy for one, the reverse, the activation energy is different. I mean, this is reactant, so all these factors come into play. But one thing is